Hi everybody, today I'm going to be talking about calculus problems that deal with the area under the curve, and these will specifically be calculus AB problems, but for those of you wondering, around 60% of calculus BC is knowledge from AB, so you'll definitely still have to know all of these problems for calculus BC. And if you don't know what I mean by AB and BC, then don't worry about it. But essentially, AP Calculus AB is usually the first year of calculus, and BC is the second year of calculus. To start off, we're going to start with a really basic problem. Here we have one function on a graph, and that function is cosine of s. The problem says to find the area of the shaded region, and for this problem, we only have to set up one integral, but we need to modify the interval that we find the area under the curve for. And what I mean by that is that when we write out our integral of cosine of s, as usual, we have to find the a and b value for the interval on the integral. Looking at the graph, we can tell that a has to be equal to 0 because the shaded region starts at the y-axis, which means that s is 0. Now that we've determined that the area of the shaded region starts where s equals 0 and goes up to some s equals b value, then now we have to find what b is. And we can tell that b, or point B, is the point where the graph of cosine of s intersects the x-axis. And the x-axis is where y equals 0. And if a graph intersects the x-axis, then that means that function has to be equal to 0. Because any point along the x-axis here, y is going to have to be equal to 0. So if we take our function, f of x, or y, equals cosine of x, and we plug in 0 for y, then we can solve for x. And this shows that our x value has to be pi over 2, which means that our b value is also pi over 2. So the interval that we want to find the area under the curve for is 0 to pi over 2. So we're going to take the integral from 0 to pi over 2 cosine of x dx. We know that the integral of cosine of x is sine of x, because if you take the derivative of sine of x, you get cosine of x. Now, using the fundamental theorem of calculus, we can evaluate this integral to show that this expression is equal to sine pi over 2 minus sine of 0. And remember, this is just our f of b minus f of a equals the integral from a to b f of x dx. This is our fundamental theorem of calculus. So now if we evaluate sine of pi over 2, we get 1 minus sine of 0 is 0. So the area under the curve is 1. Now let's move on to a different problem. And this new one has two functions on the xy plane. And let's say that we still have to find the area of the shaded region. Well, how can we find the area of the shaded region if there are two graphs? Well, let's see what happens if we take the area under the curve and subtract the two. So if we take the area under the curve of g of x, which I will color in blue, right there, and then if we take the area under the curve of f of x, which will now be in red, then if we subtract the red area from the blue area, we're only left with the green area, which is the shaded region between the two functions that we're looking for. And I'll go ahead and recolor this green area just so we can keep track of which shaded area we're actually looking for. So there you have it, subtracting the area under the curve of g of x minus the area under the curve of f of x, we end up getting the shaded region between the two. Now we'll go ahead and start our integral. We're going to take the integral of g of x from a to b minus the integral of f of x from the same interval a to b. So we set it up, but now we still have to find our a values and our b values for our interval, but each a and b value should be the same for each function. And if we go back up to the graph, we'll see that the a and b values are really where the two functions intersect each other. So right here is our a and then our b, and they're both where the two functions come together and have the same value. So now if we just set the two functions equal to each other, we'll get 4x equals x cubed. Then we can find out what x is where the two graphs are equal, where they have the same y value. So if we divide by x, we get 4 equals x squared, and then we can say that x equals plus or minus 2. And if we look at the shaded region, we know that x also has to be equal to 0. So if we go to our top expression, we see that if x equals 0, both sides are equal to each other. And that makes sense because the shaded region starts at what looks like an a value of 0. And we know that our b value has to be positive too because the b value is to the right of the y-axis, which means that we have to have a positive x value. So our a is going to be 0, and our b is going to be positive 2 because our b is to the right of the y-axis, and if it were negative 2, it would be to the left. And this is technically integral of gx of d of x. And now we can write the complete integral, so we'll write the integral of 0 to 2 g of x minus f of x. It's technically the same thing if you just combine the two, d of x. Because if you write out the integral of g of x d of x minus the integral of f of x d of x, it's the same thing as just writing the integral of g of x minus f of x d of x. It doesn't really make a difference, it's really just based on formatting, but now we can substitute our g of x and f of x equations into our integral. So we'll get the integral of 0 to 2, g of x was 4x minus x cubed d of x. Now we'll take the antiderivative of what's here in parentheses, and we get 2x squared minus 1 over 4 x to the power of 4, all on the interval of 0 to 2. And that's what this line means, 0 to 2. It just shows that you're taking the expression on a certain interval and you're evaluating it at that interval. Now we'll substitute every x value for 2 and 0, so we get 2 times 2 squared minus 1 over 4 times 2 to the power of 4 minus 2 times 0 squared minus 1 over 4 times 0 to the power of 4, which is all 0 because anything times 0 is 0. Now we evaluate 2 times 2 squared, which is 8 minus 1 over 4 times 16, which is equal to 8 minus 4, which is just still 4. So our area under the curve is 4. Now we're going to do a problem very similar to the last one. It still has two functions and we have to find the area of the shaded region. But I'm going to let you in on a little shortcut. So in the last problem, we said that g of x minus f of x would be equal to the area of the shaded region in green. And that works for reasons previously explained, but that gives us insight into a general trend for problems involving two functions. If we find the area under the curve for f of x, then we get this entire space. And if we find the area under the curve for g of x, then we only get this space. So once again, if we subtract the green minus the yellow, we get the red. But this shows that if we take the area under the curve of the function on top, in this case f of x, and subtract the area under the curve of the function on the bottom, in this case g of x, then we should get the area of the region between the two curves. So our top minus our bottom is equal to the area between the two curves. And you may look at this and say, but at these 2 points, g of x is above f of x. Well, that doesn't matter because on the interval of the shaded region, then g of x is below f of x. It only matters about the interval of the shaded region. From here onward to here, f of x is above g of x. So f of x will be our top function, and g of x will be our bottom function, so to speak. Just as already done, we will find our intervals once again by finding the points of intersection between g of x and f of x. So it says in our problem that f of x is sine of x plus 3 and g of x is x squared. Now we'll set those functions equal to each other. Sine of x plus 3 is equal to x squared, because at the points that the two functions are equal to each other, we have our a and we have our b values. Now, you might look at this and be already able to tell that you can't really evaluate this expression by hand, so I'm going to have to use a calculator. And what I'll do is I have a graphing calculator, and I will graph these two functions, sine of x plus 3 and x squared, and then I'll find the points of intersection. So I'll be right back with those intersection points. Alright, here are those points of intersection. We have negative 1.418, 2.012, and that would be this point, our A point. And then we have 1.979 and 3.918, and that would be our B point. So the only parts of these points of intersection that really matters is the x value, because our value of A and B are both actually x values. They're just unknown x values. Now we'll take the integral of our top function, as we already said, which is f of x. So sine of x plus 3 minus our bottom function, our g of x, which is x squared, from the interval negative 1.418 to 1.979. Since these points of intersections, or the a and b values, are not whole numbers, I'm just going to use my calculator, but I'll still write out the integral of our sine of x plus 3 minus x squared. We know that our integral of sine of x is negative cosine of x plus 3x minus 1 over 3x cubed, and this will all be taken on the same interval of negative 1.418 to 1.979. And I'll just write in and substitute all the points for the x values, but I'll skip ahead so you won't have to watch me write all of that out. Alright, so just in case you were curious, this is what it would all be if you had written it out, and then we're going to solve it. But I just used my calculator, and I ended up getting 7.206. And there you have it. That's the area of the shaded region between the two curves, f of x and g of x. That's all for this video. Thank you for watching, and I hope this was helpful. Make sure to keep your eyes out for similar videos coming out, because there are many types of area under the curve problems, such as revolutions of solids, which I find very interesting, and I will be making a video about next.